Section: Introduction. In this section, we explore scaling laws that suggest previously trained language models could perform better if they had adhered to a compute-optimal training approach. This approach identifies the ideal model size and training data amount for optimal performance within a specific compute budget. Many recent studies have adopted this compute-optimal training method. However, as the size of these models increases with compute, they become harder to use due to rising inference costs. This results in slower performance, higher expenses, increased battery consumption, and a larger carbon footprint, making them less accessible for academic research. With inference volumes reaching billions of tokens daily, the cost of using a language model often surpasses its initial training expenses and is expected to rise further. These unsustainable costs have led to a new training method called overtraining, where we use significantly more training data than in the compute-optimal scenario, allowing for smaller yet effective models. Overtrained models can better meet compute optimality when we consider the model's entire lifespan rather than just the pre-training phase. As we analyze supervised scaling laws, we notice that performance improvements diminish more quickly than in compute-optimal cases. To achieve satisfactory capabilities, these models require training on trillions of tokens, which is both costly and time-consuming. Our goal is to find models that can match the performance of smaller overtrained models while reducing training costs. A promising approach is distillation, where a proficient teacher model generates targets for a smaller student model. We refer to this as distillation pre-training. There are various theories explaining why distillation is effective, ranging from the transfer of dark knowledge to regularization effects. Despite the lack of consensus on its mechanisms, distillation pre-training has yielded more capable models than traditional supervised pre-training in several model families. However, some studies have indicated that distillation may produce less capable models compared to supervised methods. Given the substantial resources allocated to distillation pre-training, it is crucial for us to understand how to optimize these resources to create the most capable models possible and to determine if any advantages exist over supervised pre-training when both methods utilize the same resources. To address this knowledge gap, we conduct a thorough controlled study of distillation, examining models ranging from 143 million to 12.6 billion parameters, trained on data from a few billion to 512 billion tokens. Our findings lead to the development of a distillation scaling law, which predicts student performance based on the resources used, including the teacher model, student size, and the amount of data for distillation. We discover that the cross-entropy of a student model distilled on a specific number of tokens from a teacher model can be accurately predicted using our scaling law. The teacher's size and training data influence the student's performance primarily through their effect on the teacher's cross-entropy. We also identify a phenomenon known as the capacity gap, where a more capable teacher can sometimes lead to a less effective student. Our analysis clarifies that this gap relates to differences in learning capacity rather than just model size. Ultimately, we conclude that distillation cannot achieve lower model cross-entropies than supervised learning when both methods have sufficient data or compute. However, distillation proves to be more efficient than supervised learning under certain conditions, such as when the compute or tokens used for the student do not exceed a specific threshold and when a teacher model already exists or has additional uses beyond a single distillation. We hope that the insights and laws we present will assist the community in developing more capable models while minimizing inference costs and overall compute expenses. Section Summary. In this section, we explore the implications of scaling laws in language model training, highlighting the challenges of compute-optimal models, which are costly and inefficient for inference. We propose distillation pre-training as a promising alternative, presenting our distillation scaling law to optimize resource allocation and improve model capabilities while addressing the capacity gap between teacher and student models. Section: Background. In this section, we discuss the importance of predicting model performance as we scale up. This helps us understand the benefits of increasing our computing resources and how to allocate that compute effectively between model parameters and data to achieve the desired model characteristics. These characteristics include accurately predicting the data distribution, which we measure using cross-entropy, or performing well on specific tasks. We find that cross-entropy can be predicted based on empirical and theoretical evidence, showing that it follows a power law relationship with respect to model parameters and data, measured in tokens. The coefficients for this relationship are estimated from multiple training runs, and the selection of these runs is crucial for accurately identifying the scaling coefficients. To identify these coefficients reliably, we employ two training strategies, one where we keep the model size fixed while varying the number of training tokens, and another where we vary both model size and training tokens under a total compute constraint. We then combine the data from both strategies for our analysis. Our main goal is to predict the cross-entropy of a student model produced through distillation. This will help us determine the value of increasing compute resources for distillation and identify which distillation method yields the student model with the lowest cross-entropy for a given compute budget. In terms of notation, we define sequences and their contexts, and we focus on language modeling where our objective is to model the probability of sequences of tokens from a vocabulary. We use a next token classifier to predict the next token based on a given context, and we train this classifier to maximize the likelihood of observed data. In the distillation process, a teacher model provides a predicted next token distribution, which we use as the target for the student model. The loss from this knowledge distillation is used to optimize the student's parameters, effectively minimizing the difference between the teacher's and student's predictions. We outline our distillation scaling law by first describing our experimental setup and the necessary experiments to determine the scaling coefficients. We then discuss the form of our scaling law, find the coefficients, and verify the law through extrapolation. Our experimental setup is based on existing models and employs specific regularization techniques. We validate our approach and ensure that our models, which range in size from 143 million to 12.6 billion parameters, are trained effectively. We use the English-only subset of the C4 dataset for our experiments, ensuring that the teacher and student models are trained on different data splits. Our focus is on understanding the teacher's role in the distillation process, and we confirm that our chosen methods yield statistically similar results to optimal configurations. Section Summary. In this section, we discuss the importance of predicting model performance for effective compute scaling and the distribution of resources between model parameters and data. We outline our approach to establishing distillation scaling laws through experimental setups that vary model sizes and training tokens, ultimately aiming to identify the optimal distillation process for minimizing cross-entropy in student models. Section: Distillation Scaling Law Experiments. In this section, we discuss the experiments that generate the data needed to fit our distillation scaling law. This law helps us estimate the student cross-entropy, which depends on various factors including student parameters, the number of distillation tokens, teacher parameters, and the number of teacher training tokens. As mentioned in the background section, only specific data combinations can reliably identify the scaling law coefficients. To gather data for our scaling law fit, we combine three experimental protocols. First, we assume that training a student using a teacher's signal is similar to training on a fixed dataset. We expect to see power law behavior in the relationship between student and teacher parameters when using a fixed teacher. To accurately identify the coefficients, we follow a protocol similar to the chinchilla protocol, but we need to use multiple teachers since the impact of student size and tokens on performance can vary across different teachers. To maximize the variety of teachers within our compute budget, we trained 6 chinchilla optimal teachers with sizes ranging from 198 million to 7.75 billion parameters. We then distill these teachers into students with 4 different isoflop profiles, focusing on standard training costs. The resulting student cross-entropies are shown in our figures. Interestingly, we find that in some cases, students can outperform their teachers, indicating weak to strong generalization, which we explore further in another section. Next, we address the limitations of the fixed teacher and isoflop student protocol, which does not adequately reveal how teacher parameters influence student cross-entropy. To better understand this, we fix the student parameters and vary the teacher parameters while adhering to a compute constraint. We distill into 4 chinchilla optimal students, and the resulting cross-entropies are presented in our figures. Finally, we conduct experiments with fixed teacher and student combinations to observe how student cross-entropies vary across a wide range. We train 10 teachers and students of 5 sizes, with multiple choices for each student. The results for 2 of the students are included in our figures. We also observe a capacity gap, where improvements in teacher performance do not always lead to better student performance and can even hinder it. This phenomenon, known as the capacity gap, is common in distillation. We analyze how the student struggles to model the teacher's capabilities and provide explanations through kernel regression and synthetic settings, marking our first controlled demonstrations of this gap. To determine the functional form of the distillation scaling law, we note that the contributions from teacher size and pre-training tokens can be summarized by the teacher's cross-entropy. We propose that the student cross-entropy follows a broken power law in relation to the teacher's cross-entropy and a power law concerning the student parameters. We outline the properties of our scaling law, including that an infinitely capable student can model any teacher, random teachers yield random students, and that a capacity gap exists. We also describe a transition between 2 power law regions, where the student can be either a stronger or weaker learner than the teacher. We aim to fit positive coefficients based on the data produced in our experiments. Section Summary. In this section, we describe our experiments to gather data for fitting a distillation scaling law, which estimates student cross-entropy based on various parameters of both students and teachers. We employ 3 experimental protocols to explore the effects of teacher and student configurations on performance, revealing phenomena such as the capacity gap, where increased teacher capability can hinder student performance, and propose a broken power law to characterize the relationship between student cross-entropy and the relevant parameters. Section: Distillation Scaling Law Parametric Fit. In this section, we utilize the teachers for fitting our supervised scaling law and gather all necessary data for our distillation scaling law. We detail our fitting process and present the resulting scaling coefficients. Our supervised and distillation scaling laws align with observations, achieving a relative prediction error of 176, even when we extrapolate from weaker to stronger models. Additionally, we verify that for a fixed model size, distillation in an infinite data scenario aligns with supervised learning on infinite data. Next, we apply our distillation scaling law to explore various scenarios. Typically, the resources for distillation pre-training include a compute budget or a dataset with a certain number of tokens. We approximate the compute cost for the distillation process, considering the costs associated with teacher logit inference and teacher pre-training. We note that the number of floating point operations a model performs during a forward pass is significant, especially for smaller models with large context sizes, where the contribution from attention is notable. To address this, we derive a straightforward expression for fixed aspect ratio models and suggest that the scaling community adopt this hyperparameter setting. To understand when distillation may be beneficial, we compare its performance in the best-case scenario against supervised learning. We overlay data onto contours of distilled cross-entropy compared to a supervised model with the same resources. We find that supervised learning consistently outperforms distillation when sufficient student compute or tokens are available. While distillation is advantageous with a modest token budget, supervised learning excels when a large number of tokens are present. This aligns with the expectation that supervised learning can identify the best solution limited by model size, whereas distillation is constrained by the distillation process. We then shift our focus to the common scenario of planning to distill and choosing between existing teachers. A larger teacher may offer a better learning signal but comes with higher costs due to teacher logits. Given a target student size and budget, our only variable is the choice of teacher. For a fixed data budget, as student size increases, the teacher's cross-entropy should decrease following a power law. We illustrate student cross-entropy at different distillation token budgets and observe that the optimal teacher loss decreases as a power law with student size until it matches a certain point, leading to a sharper decrease in teacher loss. This observation supports the idea that optimal teacher scale generally follows a linear scaling with student scale across various model architectures and data scales. Importantly, our findings indicate that teacher cross-entropy determines student cross-entropy, rather than the compute budget itself. We further explore a fixed compute budget setting for teacher inference. Section Summary. In this section, we detail our fitting procedure for the distillation scaling law using teacher models, achieving a relative prediction error of 176, and confirm that distillation aligns with supervised learning in the infinite data regime. We explore the trade-offs in distillation scenarios, highlighting that while distillation can be beneficial with limited tokens, supervised learning generally outperforms it when ample data is available, emphasizing the importance of teacher model selection in optimizing student performance. Section: Compute Optimal Distillation. In this section, we extend the analysis of previous work to focus on distillation. Our goal is to determine how to create a student model of a specific size with the lowest possible cross-entropy while adhering to a compute budget. We examine various scenarios to understand the best and worst cases for incorporating teacher inference within these compute constraints, comparing our findings to optimal supervised performance. To find the minimum values, we use constrained numerical minimization techniques. We observe that supervised learning consistently matches optimal distillation when we have enough compute resources, and this advantage for supervised learning increases as the student model size grows. Our analysis shows that smaller models tend to benefit more from supervised pre-training, while larger models gain more from distillation. When we include teacher training in our compute budget, we find that the best student cross-entropy is always higher than in the supervised learning scenario. This suggests that if our only goal is to create the best model of a target size without access to a teacher, we should opt for supervised learning rather than training a teacher first. However, if we aim to distill into multiple models or use the teacher as a server model, distillation may be more efficient. We also explore the most complex scenario of teacher pre-training and inference. Our findings indicate that both student and teacher tokens scale in a power law, with student tokens increasing at a faster rate. Initially, the optimal teacher size grows until it slightly exceeds the student size, after which it levels off due to the high cost of inference with large teachers. This leveling off occurs because, as the number of student tokens increases, it becomes more efficient to overtrain the teacher. We summarize these trends and configurations in our detailed discussion, providing insights into how different quantities interact within the compute framework.